All right, Chem 11. Welcome to our next lecture. It is representing chemical reactions. It is the first lecture of our second unit, which is chemical reactions. So it's a good place to start. As usual, we have our online PowerPoint lecture notes up here on the iPad. And then we've got the whiteboard to help us out with some extra stuff as well that'll help strengthen our understanding. All right? So let's begin. So what is a chemical reaction? Well, a chemical reaction describes a chemical change. In grade 9 and 10, you learned about two types of changes. There was the physical change and the chemical change. Now, in the physical change, which is not really the focus of what we're doing today, but we'll talk about it anyway. The physical change, the substance did not change its formula. All it did was change its state or change its form, right? So for example, if I take a hockey stick and I go to take a shot and the stick breaks in half, it didn't become a new substance with different properties. It just became a two-piece stick, right? Instead of one. The materials in the stick are still the same materials. I just have two pieces of it. Or think of an ice. If I take ice and I melt it, well, the formula for ice is H2O, and the formula for the liquid is H2O. And if I take that liquid and boil it and make vapor, it's still H2O. The formula hasn't changed. So the makeup of the substance hasn't changed, and the properties have not changed. In a chemical reaction, the substance that we start off with in the reaction or the change is not what we end up with. We end up with a different substance with a different formula and different properties altogether. That's a chemical change, all right? And chemical reactions are when chemical changes occur, all right? The substances that enter the chemical reaction, that begin the reaction, are the reactants. And the substances that finish the reaction, that are formed in that reaction, are called the products. So the general format of any chemical reaction is right here. We have reactants that go on to form products. This yield arrow means these things react and form these things. The reaction between reactants, what we begin with, yields or produces these products, the things that we finish the reaction with. Now, how do I know a reaction even took place? Well, there are 4 observable signs, right? Things that I can notice with my senses, that I can see, that tell me definitely a chemical change has occurred. Any chemical reaction is going to have at least one of these, maybe more than one, right? Quite often more than one. So the first one is a color change, right? Leaves changing color in the fall. That's because there's a chemical reaction taking place inside of the leaf, right? Heat or light being emitted. Now, emitted is the fancy way of saying given off. So if heat or light's given off, chemical reaction is taking place there. Gas emitted or given off, right? Usually we see this as bubbles. Or precipitate forms. Now, a precipitate is a solid formed from 2 fluids. So to use this model, we have 2 fluids that enter the reaction. Now, what's a fluid? A fluid is a gas, a liquid, or an aqueous solution. It is not a solid. And what happens is those 2 fluids react to produce a solid, or precipitate. Right? That precipitate is a solid. There is no solid that went in here, right? 2 liquids mixed, or a gas and a liquid, or whatever it was. Any combination of these 2 states goes in and it produces a solid. Now, if one of these things was a solid to start off with, if one of our reactants was a solid, then it's not a precipitate. You already had a solid going in. It has to be a brand new solid that came from 2 fluids. That's what a precipitate is. Now, some teachers will call it a 5th sign of a chemical change, but the 5th sign is that it's difficult or hard to reverse, or impossible, right? It might be irreversible. That's something we're not really going to go with. Now, many reactions are difficult or impossible to reverse, right? We burn a log in our fireplace. We go back after the log is burned and there's ash and soot. We're definitely not getting that log back, so that's irreversible. right? The leaves decomposing in the fall and changing color. We're not getting the green leaves back, right? But there are reversible reactions that can successfully go from reactants to products and then back. Our blood maintains its pH using a blood buffer system that constantly swings back and forth between two different substances. So using irreversible as a bona fide thing, yeah, a lot of them are, but not all of them. So we're not going to use it as a definitive sign of a chemical reaction. Plus, it's difficult to see that as well. Now, there are three ways to represent a chemical reaction: word equations, skeleton equations, and balanced chemical equations. The word equation simply uses the written names of the substances involved as reactants or products in the reaction, right? So for the decomposition of water, I'm just going to erase this very quickly. For the decomposition of water, that's very easy. We would have water, and it decomposes, right? It decomposes into hydrogen gas and oxygen gas. Basically, it breaks down into its component elements, right? Water is H2O, and it breaks down into a gas made of H's and a gas made of O's. That makes sense, right? Now, from our word equation, we can derive a skeleton equation. And all a skeleton equation is going to do is it's going to take each of these names and change it into its formula. So for water, we would have H2O. This still comes down. Hydrogen gas we know is diatomic, and so is oxygen gas. So there is our skeleton equation. All right, word equation in black, skeleton equation in blue. All right, so this is why we harped on you. You got to be able to go back and forth between names and formulas and names, right? Because we knew we were going to have to do this in the second unit and throughout the rest of the course and all through grade 12 and university if you take anything chemistry. All right? So the ability to go from names to formulas is so important. And we have to get these formulas right? If I mess up a formula, basically it's not that substance anymore. Each substance has its own particular formula. And if I don't get it right, I've really made something else, not what I intended, right? So I simply translate each written name into its proper formula. So just like that. Now, skeletons are cool and all, but they have a problem. They break a very important law in chemistry, and that law is called the law of conservation of mass. And it basically says mass in a chemical reaction, it can't be created, it can't be destroyed. So whatever mass you start out with over here in your reactants, you have to have the same mass over here in your products, right? Think about what has mass. Matter has mass. Matter's made up of atoms. So basically what it's saying is, hey, the same amount and type of atoms that you have going in, they have to come out, right? I can't start with 5 carbons over here and end up with 10 carbons. Or in this case, I can't start with 2 hydrogens here and end up with 13 hydrogens over here. Well, where did those other extra hydrogens come from? Oh, I don't know, just made them up, right? We can't do that. And we can't just make them disappear either, right? If we could just make up atoms, I'd go, bam, gold. And gold would be all over the place so I could retire early, right? Or that pesky student in class that's always giving me trouble. Bam, disappear. And the atoms making up that student would disappear and I wouldn't have to deal with them anymore. I wish. But the law of conservation of mass is keeping me poor and keeping that student in my class. All right? So the mass of any one of the elements at the beginning of the reaction has to be the same at the end of the reaction. All right? So if I have 5 carbons going in, 5 carbons out. 2 hydrogens in, 2 hydrogens out. All right? It's also known as the law of conservation of matter because it's talking about the number and type of each type of element or atom, and that makes up matter. So the same amount of matter that goes in has to come out. It doesn't have to be connected to the same stuff. I can rearrange the elements and they can have new partners and form new compounds. But again, if 5 carbons go in, 5 have to come out. 4 oxygens go in, 4 have to come out. I can't alter the numbers. I can't add stuff or take it away. Conservation literally means to keep it the same. Don't change it. Like a conservation area for wildlife. We don't go in and plow over the forest, right? We don't alter any of the landscape. We leave it the way it is. It stays the same. So, let's check that skeleton equation for water again. We have it right here in blue, right? Let's check out our elements to see who's following the law and who's not. If I look at hydrogen, I've got 2 hydrogens going in and 2 coming out. Hey, hydrogen's following the law. Good for hydrogen. But the O's, they're not. Water only has 1 O, and suddenly there's 2 coming out. So an O materialized out of nowhere. That can't happen. So we have to fix it, right? And what we do to fix it is we use coefficients. I'm going to put coefficients in giant letters down here. The reason for that is every so often somebody will use a subscript. Look, 3 exclamation marks. That means coefficients are really, really, really important. Don't mess around with them, all right? They're the big numbers, and they go in front of formulas, all right? So in our skeleton equation, we've got to add a coefficient here to fix our oxygens. Remember, 2 hydrogens, 2 hydrogens. Awesome. 1 oxygen, 2. Not so awesome. So I'm going to put my coefficients in with red. I'm going to draw this down here again so we can have an example of our skeleton equation. And this bottom one, this second one here, will be our balanced equation. So the 4th rule of Chemistry Fight Club is don't touch the subscripts or else, all right? Every so often what someone will do, and this is entirely wrong and should not be done, they'll go 2 H's, 2 H's. Good. 1 O, 2 O's, and they'll do this. No, 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 no. That little number and this one and this one, and they're subscripts. We don't touch the subscripts. I'm supposed to have water. Yay, water. Boo, hydrogen peroxide. I drink this, it's refreshing and nice. I need it to stay alive. I drink this, I am dead. Not as refreshing, right? And all it was changing the little 1 here that we don't see into a 2. Not a big change, but a big change, all right? So don't touch the subscripts, for God's sakes, all right? How are we going to fix this? We're going to use coefficients. So 2 H's, 2 H's. 1 O, 2 O's. So I'm going to put a big 2 here. The 2 has to go at the front. Do not put a big 2 halfway through a formula. We do not break up formulas. All right? I'm not putting a big red 2 in here. The 2 has to go in front of the thing that I need to bring up. Here's 2, here's 1. I've got to boost that up to a 2. So now I have 2 oxygens and 2 oxygens. But I have to go now and balance my hydrogens again, because now I have 2 times 2 hydrogens, which is 4. Here I've only got 2, but that's an easy fix. I put a 2 there. And now everything is balanced. 2 times 2 is 4 H's. 2 times 2 is 4 H's. 2 oxygens, 2 oxygens. All right? Use coefficients. For God's sakes, don't be one of these chemistry hooligans that's going to go live by your own laws and rules. Don't touch the subscripts. And that's right, kids. I went there. Or else. That's not a warning. That's a threat. So there's our example there, right? If we change the slightest little coefficient, the slightest little subscript, it changes the formula. We don't want to do that. We want to keep our substances the way we intended them to be. So those formulas can't change. So coefficients only. So here we're going to do some practice, and here's our first one. We just did this one, but I'll bring up another one here, and we'll go through it very, very quickly using only coefficients. Now, normally in my class, this would be up on the screen and I would be able to do it with you live. But I'll do a couple of them right here really quick. So here's our first one, right? We already did the water one. So I'd simply start off with 1 aluminum, 1 aluminum. 3 chlorines, 2 chlorines. Now this is very common in chemistry. We see 2 and 3. Whenever we end up with 3 on one side, 2 on the other, or 3 on this side, 2 on that side, vice versa, whatever, we change it into the lowest common multiple, which is 6. All right? So that means a big 3 here, 3 times 2 is 6, and a big 2 here, 2 times 3 is 6. And then I have to start over again at the beginning, because sometimes fixing one thing alters something that we already thought was fixed. So 2 aluminums, 1 aluminum. 2 aluminums, 2 aluminums. 2 times 3 is 6 chlorines. 3 times 2 is 6 chlorines. 1 magnesium, 3 magnesiums, but that's an easy fix. So that one is done. All right? Our next one. Oh, I like this one. This is propane, like in a barbecue. C3H8 plus O2. This is a combustion reaction. This combustion reaction makes food on the barbecue. All right, so 3 carbons, only 1 carbon. I'm going to put a 3 there. 3 carbons, 3 carbons. 8 hydrogens, 2 hydrogens. 4 times 2 is 8, and there's 8. So far, so good. 3 C's, 3 C's. That 2 belongs to the O, not the C. 3C, 3C. 8 H's, 8 H's. O's. I got 2 going in. Here I've got 3 times 2, which is 6, plus 4 times 1, which is 4. That's 10. So I got to make this 10. 5 times 2 is 10. All right? The next one, zinc chloride plus K3PO4, that's potassium phosphate, makes zinc phosphate plus KCl. All right. So for this one, 1 zinc going in, 3 zincs coming out. I'll put a 3 here. 3 zincs, 3 zincs. 3 times 2 is 6 chlorines, only 1. 6. 3 zincs, 3 zincs. 3 times 2 is 6 chlorines, 6 chlorines. 3 potassium, 6 potassium. 2 times 3 is 6. 2 phosphates, 2 phosphates. Whenever I can, I try to treat the polyatomic as one type of atom or one thing. So 2 of these phosphate groups, 2 of the phosphate groups. All right? And our last one, I know you've done this stuff before, but it is vitally important to this unit. We have to be able to balance equations and do it quickly and easily. All right? So let's take a look at this one. 2 sodiums, 2 NAs, 2 NAs. So 2 sodium, 2 sodium. Again, I'm going to try to keep this together. 1 sulfate thing, it's not 4, that 4 is part of the sulfate. So 1 sulfate, 1 sulfate, good. Calcium, calcium. 2 nitrate clusters and 2 nitrate clusters. So that one's balanced with just that simple 2. All right? Now, the yield arrow. We can add stuff to that yield arrow. If you need to get these down, pause the video. I'm going to erase them. So the yield arrow. We can put different things on that yield arrow that help tell us about the reaction. All right? So for example, if we were to use a Bunsen burner to heat up some stuff in a test tube, but we didn't know the exact heat, we just knew we had to heat it up to get the reaction to go faster, we would use a delta sign above the arrow. And that would tell the person that's familiar with chemistry, hey, we had to heat that up to get it to turn the product. Or if we know the exact temperature, like a hot water bath where we have a dial that tells us the exact temperature and we set that dial, we can put that above it. All right? Both of those explain heat. This heat, I don't know. I just know I heated it up. This one, I know the precise amount. I might have a catalyst, right? Or an enzyme, which is an organic catalyst. And that helped me. In that case, like for photosynthesis, I know I need chlorophyll. So I can write chlorophyll here. The chlorophyll is not one of the products. It's not a reactant, but it helps turn reactants into products, right? Or I can use the name of a type of energy. I need sunlight to do this. Sunlight is a form of energy, and energy is not made of atoms, so it can't be a reactant, can't be a product. And sometimes in chemistry, what we'll see, very similar to our temperature, if we're using gases, we'll see the pressure. So we might say it was done at 100 kilopascals, or so many millimeters of mercury. That's an older way of measuring pressure. But kilopascals is the more modern unit. So if I'm working with gases, I might write the specific pressure above that. All right? Anyway, that's all I got for today, I believe. There's Drake, always a chemistry fan, telling us, hey, don't be a jabroni. Don't use subscripts to balance your equation. Be cool like Drake and use those coefficients. Anyway, that's all I got. If you have any questions, comments, or concerns, please leave them in the comment section below the video, or reach out to me through ESB if you're one of my students, and I'll get back to you as soon as I can. Hope the lecture helped. I'll see you soon. Bye-bye.